All right, everybody, we're here to look at question 10, the final problem from our practice test. So we have a certain beverage company is suspected of underfilling its cans of soft drink. The company advertises that its cans contain on average 12 ounces of soda with a standard deviation of 0.4. First of all, we'll write out things that we know. We know that the mean of the population is purportedly 12 ounces, and the standard deviation, sigma, is about equal to 0.4. Now, these are parameter values because they are meant for the entire company. Nowhere does it say that this is a normal distribution. It just says that we have this mean and we have this standard deviation. So part A says we're going to calculate or compute the probability that a random sample of 50 cans produces a sample mean fill of 11.9, or I should say a sample mean fill. No, a sample mean fill of 11.9. Some notable things here. This 50 is a sample size. It's greater than or equal to 30. Therefore, by CLT, we know that the shape is approximately normal. That's the shape of the sampling distribution is approximately normal. We're going to need to know that because we want to know, we were going to want to get some probability here. I've gone ahead and I've picked out a nice normal curve. My only complaint here is that the z-scores are at the bottom. That's okay. Usually I put the z-scores on top of the curve. The sample mean, or the mean of this, should be 12 ounces. Because the mean of the sampling distribution for X bar is that the mean of the population, which we were just told is 12 ounces. The standard deviation of the sampling distribution for X bar, that's the standard deviation of the population divided by the square root of the sample size. So we'll compute that right now. We got a 0.4 divided by root 50. Let's clear this out. This is getting really messy. 0.4 divided by the square root of 50. That's 0.056, 0.057. Okay. Now, our standard deviation was given at 1 decimal place, so we could make this a 0.06 or 0.057. I'm just going to leave it as 0.057. I feel more comfortable with that number. Just having one significant figure just feels kind of weird. So we'll just keep it at 2 significant figures. Okay, so that means that here at 1, we have, that's going to be a fill of 12.057. And 2 standard deviations would be 57 multiplied 50 114. Okay. Over here at -1, I don't know if we're going to need that, but we might as well do that. That's going to be 12 minus 0.057, and it's getting late, and I don't want to do this in my head anymore. So 12 minus 0.057, that is 11.943. And then subtract another 0.057. That's going to be 11.886 for 2 standard deviations. Okay, so that should be more than enough curve for me to do my sketch. This is a sampling distribution for X bar. Sampling distribution for X bar. Okay, so The first thing we're going to need to do is get a z-score. So the z-score is going to be equal to 11.9 minus 12, the whole thing divided by 0.057. Before we compute that z-score, maybe I should find out where 11.9 is on my normal curve. And, well, that should be somewhere between 11.8 and 11.94. Let's pretend that it's right in the middle here. Okay, that should be 11.9, somewhere over there. So I should see a z-score somewhere between -2 and -1. Hopefully my maths works out correctly. Let's get to the calculator. 11.9 minus 12 divided by 0.057, -1.754. 1.754. So yes, we are correct here. Which way do we shade now? We want to go 11.9 or less. So that means we want to shade to the left of that, because less means to the left, of course. So we want that area. If you're estimating, you know that the area here, this is 0.5. And you know the area all the way over here is 0.16. So we're looking at an area that's bigger than 0.05, less than 0.16. That should be the correct answer. So let's see. The probability sample average fill is less than 11.9. That's going to be equal to a normal CDF, where the lower is negative infinity, really. Actually, we can say it's 0. The upper is equal to 11.9. The mean is equal to 12. And the standard deviation is equal to 0.057. And that should give us our answer. Let's take a look at, well, let's do this. We're going to go to distribution, number 2, normal CDF, your friend and mine. The 0 is our lower, our upper is 11.9, our standard deviation was 12, and our mean was 0.057. That gives me a 0.0396. 0.0396. Okay, let's move on to letter B. Suppose that 25 students in a statistics class collects a random sample of 50 cans and calculates the mean number of soda ounces. Describe the approximate shape and distribution for these 25 values of X bar. So this sounds kind of weird, but we are, so 25 cans each. So we're actually making a sampling distribution. It's not the complete sampling distribution, but it's close. It's a lot of them. So we have a sample size. Sample size equals 50, which is greater than 30. So CLT says the sampling distribution is approximately normal. That's our shape. Our mean of the sampling distribution, our mean of X bar, that's going to be the same thing as the mean of our oh wait, no, we just want to get the approximate shape. So we have the approximate shape. That approximate shape is approximately normal. If we did want to go further, of course, the mean is going to be equal to 12 because that's the mean of the population, and the standard deviation is going to be equal to the population standard deviation. I don't remember, it's 0.4 divided by the square root of the sample size, and the sample size was 25. That's 0.08. Which seems different than your answer key. Oh, I'm sorry. You know why? Because the sample size is 50. We're taking a sample of 50 cans. My mistake. Yeah, 0.056. It's really 57. Okay, so that's our letter B. Let's take a look at letter C. What important principle do we need to use here? Well, that important principle is going to be the central limit theorem. Okay. So in a sampling distribution for x bar, the shape of the sampling distribution will be approximately normal for large sample sizes. And how large is a large sample size? Well, that's about n greater than or equal to 30. Okay, so that's our central limit theorem. Letter D, we're going to use the 68, 95, 97 to find an interval that contains the middle 95% values of x bar. I'm assuming we're still using that same thing. So you should remember from that 95% is the second standard deviation in a normal curve. So we're basically looking for two standard deviations above and below. So if our standard deviation is 0.4, we have to do this in the sampling distribution. So in our sampling distribution, what was it was 0.057. So two standard deviations. That's going to be 2 times 0.57. So two standard deviations. That's going to be equal to 2 times 0.057. And that's equal to, why did it not multiply? I think I need to do that. Okay, 0.114. So if we do 12 plus 1.114, okay, and then 12 minus 0.114, it's 11.86. So that is, we could put that here, 12.114 and 11.886, which reminds me that I think we did that already. Yep, there it is, 12.114 and 11.886. So about 95% of sample means the sample size of 50 will have a sample mean, or will be between 12.114 and, no, I got that backwards, 11.886 and 12.114 ounces. Okay, and we can finish this off now with letter F. Can you calculate the probability that a single randomly selected can contains 11.9 ounces or less? If you can, do it. If not, explain why you can't. Well, the problem is we don't know anything about the shape of the sampling of the population. We don't know anything about the shape of the population, so we cannot compute this. You're tempted to say that the population is approximately normal, but if you look back at what we have here, there's nothing that says that the population is approximately normal. The fact that we can use a normal distribution at all in this problem is a function of the fact that we have a sample of 50 rather than we're looking at a single can. So that sample of 50 allows us to use normal CDF. And that is all of this question. It was a long one, and good luck on your test, everyone.